Hi, my name is Nolan Benner, and here's my smiling face. And here you can see our circuit, which is a voltage-controlled oscillator. Essentially, what the oscillator does is produce a certain signal frequency depending on what the control voltage is set to. We adjust the control voltage manually in order to produce different frequencies for our triangle wave and square wave outputs. How it works is that the control voltage is input here and goes into these two resistors, which are connected to the positive and negative terminals of the first op amp, which is an integrator. The voltage at both the positive and negative terminals of the op amp are designed to be half the control voltage. This specific voltage at the positive terminal is set using the voltage divider. Current flows into this 100 kilo ohm resistor in order to give the input voltage at the negative terminal to be half the control voltage. The turning on and off of the MOSFET allows for the oscillating change in the output voltage signal of the integrator. The MOSFET is on when it has a positive applied gate voltage, as this creates an electric field that allows electrons to move in the region below the gate. When the MOSFET is on, the current from the 100 kilo ohm resistor goes into the MOSFET. At the same time, the capacitor provides additional current to give the 51 kilo ohm resistor the same voltage drop as the 100 kilo ohm resistor, which charges the capacitor. The op amp outputs a linearly increasing output voltage to allow for this current through the capacitor. This gives the rising half of our triangle wave. When the rising output voltage reaches 10 volts, which is the upper threshold of our Schmidt trigger, the MOSFET turns off because it no longer has a positive applied gate voltage. When the MOSFET is off, the current from the 100 kilo ohm resistor can no longer go through it and instead goes through the capacitor, which discharges it. For this to work, there must be linearly decreasing voltage at the output of the integrator op amp. This gives the falling half of our triangle wave. When this output voltage reaches 0 volts, which is the lower threshold of our Schmidt trigger, the MOSFET turns back on and the cycle repeats. The oscillation of rising and falling voltages at the output of the first op amp when the MOSFET is on and off respectively gives the triangle wave that we measure. This triangle wave is then used as the input of our second op amp, which gives the square wave ranging from positive 15 volts to about negative 15 volts when the Schmidt trigger is activated and deactivated, which my partner Josh will explain.
Hi, my name is Joshua Punnoose, and here's our voltage oscillator. I'll be talking about the Schmidt trigger, which is over here. The Schmidt trigger is turned on when the voltage at the positive terminal of the op amp is greater than the voltage at the negative terminal, and when the Schmidt trigger is activated, it is attached to the MOSFET shown over here, and when it's on, it turns the MOSFET on and allows current to flow across the MOSFET.
And Demo here with our lab group. We see that the first op amp outputs a triangle wave, and this is usually the input for the Schmidt trigger, which creates a square wave based off of that, and this is where an oscillation occurs. We see right here that the frequency is 135 hertz. Now if we adjust the voltage, so right now we're turning it up, and we see that the frequency increases linearly, and if we turn it down, then the frequency goes down. And this is a linear relationship, as we'll show on the graph. If we take a look at the LT Spice simulation, we see that the output of the first op amp is the same sawtooth triangle wave, and the V out gives us a square wave that oscillates depending on the input voltage, just like we saw in the experiment. So if I turn down the voltage to 3 volts instead of 5 and run it again, we should expect the frequency to decrease, which it just did. So the experimental results they coincide with the theoretical simulation. The only discrepancies we might have is that we're using the universal op amps and a MOSFET that is similar but not the same as the op amps and MOSFETs that we're using in the experiment, just because LT Spice doesn't have those correct models.